I was actually a postdoc for 3 years at UCLA Math Department, and this is my second year in Wisconsin, so it's really great to be able to escape the Wisconsin winter just for a short period of time here. All right. Okay, so these are my collaborators related to the works that I'm going to be presenting today. Yeah, most of them I met in UCLA. It's been great pleasure to work with all of them. Still, a lot of projects are going on with them. Okay, so the key concept that I want to deliver today, is low-rank mesoscale reconstruction. So there are 3 words. I'll explain those 3 words in the context of image and networks. Okay, so as a motivational problem, let's think of this problem. Okay, so we're given this image A, and you're also given another image B, and let's try to make a reconstruction of this image A so that at this k by k local level, the shape or style of this image resembles this image in B. So there are a lot of deep learning models like was it Deep Dreams or some other models that does it, but I want to do it using linear algebra in this case. So this is a naive version of the reconstruction that resembles, there's as close approximation of image A that uses local structure of B. So I'll explain how to do this, and we'll generalize to this network case. So if you have an image, you can think of it as a 3D tensor, A by B by 3. And if you have a k by k window, you can think of it as a sub-image of size k by k by 3. It looks like this square image like here. And we can try to approximate this sub-image by the same shape, the tensor, using some knowledge on the image B. So let's say we use a simple linear model. We use a linear combination of some basic images L1 through LR, and these basic images are somehow learned from this reference image B. So once you learn it, you try to fit those R basic images to approximate what you see in the image you want to reconstruct. Okay, so you can do this at every local level. So if you want to reconstruct the whole thing, you do it everywhere and patch them together. So let me show you how it works. So we are randomly sampling this k by k window in the image, and every time you do it, you're going to try to approximate that by using this basic pieces you learned from B, and then try to patch them together in the original image A. Okay. So the result is not as sharp as the original image, but it becomes black and white because the reference image B was black and white, and it kind of resembles at the local level what you see in the reference image. Okay, so it's a version of the original image that uses this mesoscale or intermediate scale structure of the reference data. Okay, any question up to this one?
Your learning is it color? You say k by 3, but that original image looks grayscale.
Right. That's because the reference image was grayscale.
Okay.
Yeah.
So your basis terms are also grayscale, I guess.
I mean, you can still think of this guy as a 3D tensor, but just a black and white.
Repeated.
Yeah.
Sure.
Yeah.
Okay.
So the basic shapes are preserved, but the colors are lost. Okay. So there are some questions that we can ask. This is a very classical, traditional. Yeah. Oh, sorry. Go ahead.
I don't see in the resulting image. I don't see that there is the brightness bias from the bottom to the top.
Right. So yeah, great. Yeah. So there are a lot of structures that could be preserved, and also could be lost. For example, the colors are lost, and the hues are lost, and the shades are like almost preserved. So what we are trying to see is not to get very good approximation of this, but we are trying to approximate this using the structure that we see in the B. So it's a way of transferring our knowledge in B and how good of a feed you can get of approximating A. Yeah.
So why is there no sketch marks in the in the image 8-ish?
Yeah, I ran this simulation last night, so I had to stop at some point, but it's still running. Yeah, so yeah, yeah. If you keep sampling, then yeah, those black.
But do you think you would get these brush marks or pencil marks?
Oh yeah, yeah.
You don't see them in the.
Right. So yeah, So those brush touches are characteristic of the original image.
But I mean the ones from B.
Oh yeah. Right. So I only use like 10 basic images. It's a very low rank approximation of the original image. So we learn very few number of basic shapes from here, and then use that to approximate here. So if you use a larger number of elements or basic shapes from B, then you can get more accurate reconstruction of this. And also the K I chose to be 20. And at 20 by 20, you don't quite see so this image is actually quite big. So at 20 by 20 scale, you don't see too many fine lines. Yeah.
These are very broad questions, except for that type of application in like changing the style of an image.
Yeah.
Could you give us a couple examples where that type of algorithm would be used in like other applications? It seems interesting, but I cannot pin examples of application beyond image like.
Yeah. So I'll do exactly this thing for networks. And that means we can try to transfer mesoscale or subgraph structure for one network and reconstruct the other network. So that we can use it as a means of comparing two networks at the mesoscale level, and also you can use it to denoise. So for example, if you have some knowledge on the clean network, and if you have a corrupted network, then you can try to reconstruct this corrupted network, and then what you get out of it is a clean version of the network. Yeah, great. All right, so we'll have this question in mind. So algorithmically, it's pretty straightforward, but can we theoretically guarantee how can we bound the error between original image A and the reconstructed image A hat as some function of the scale you're working on, the K by K, and also how good of an approximation you can do at scale K. Okay. So we'll talk about this. And then the second question is, how do we learn this best or basic images from the reference image B? So this is related to dictionary learning structure, algorithm. And also we can leverage tensor structure. So a lot of these classical algorithms are based on vector valued sequence processing, but a lot of modern data has multi-modal structure. So if you can incorporate this tensor-based learning algorithms in this case, it's going to be more storage efficient and also more meaningful. Okay. All right, so I'll move on to networks. So I want to draw a parallel story for networks. So just very simple version of network. We have a bunch of nodes connected by edges. There's no direction, there's no weights. So very simple. You can represent this network as a simple graph like this, or as an adjacency matrix, where ones are, the entry I comma j is the indicator that there's an edge between I and j. Okay. So there are in a lot of domains, a lot of relational data are produced and stored in the form of networks, and the volume is huge. So it's going to be really nice to develop a very nice structure analyzing algorithm for networks, and then so that's the main motivation for this one. So let me show you a couple examples of networks, real-world networks. So now on the left, we have a coronavirus protein-protein interaction network. So each node is a protein. And edge means these two proteins represented by the nodes have a common interaction. So there seems to be some proteins that are interacting with a lot of neighbors, but these neighbors are not really interacting with any other. On the right, this is an archive collaboration network as part of it. Okay. Each node represents an author, and edge means there's a collaboration between those two authors. Okay, so in the classical network science or network data analysis, we usually use some random network model to fit to a given network and then try to infer some structure out of it. So, for example, very well studied field or technique is called community detection in networks. So you basically want to cluster or group the nodes together so that you see more edges inside the group and fewer edges outside of the group. Okay, so once you do that, you can kind of, this is kind of a low-rank approximation of this big graph. Even though there are so many nodes, there are only like 5 clusters, and you can think of it as basically a 5-node graph in some high level. Okay? So there's a model like that in the field. It's called stochastic block model, very basic model. So you have 5 different clusters. You assign some probability of having edges inside the cluster and out in between the cluster, and try to fit the parameters of this model to the given network. Okay, another feature of the network we want to try to fit or detect is called hub nodes. This is a characteristic of a social network. So it's a node that has a large degree in comparison to the other nodes. And there's a random network model for that. It's called preferential attachment model. And it's well known that it can model this power law degree distribution, and it's a very good model for the social network, which are obtained by growing dynamically. All right, so given real-world networks, we can try to fit some random network model that are constructed at the bottom level. So we specify at the local level how these nodes are connected together. We need to assume some mechanics of it. And then try to fit the models to the real-world network. And then try to infer some global or local structure of the real-world network. So that's a traditional pipeline. But there are many drawbacks for this traditional model-based approach, because it requires to have a lot of different random network models. What if the phenomena or structure you want to analyze about the network is not captured by one of the classical random network model? Or what if the parameter estimation is too expensive, and so on. So instead, can we somehow do a data-driven approach? So can we learn some mesoscale learning from the network and then get some rough idea of how the network looked like in the mesoscale, and then try to use that information to reconstruct or go back to the global analysis. Okay. So we've seen this example in images already. So if you have a big image, then by the way, mesoscale is a terminology that refers to some scale that sits between this local and global scale. So a characteristic feature is that it's still large enough to have a rich structure, but it's still small enough so that you can sample a lot of them so that you can do some statistical analysis. Okay, so it's a nice happy medium. So for images, we can think of this mesoscale structure as k by k sub-images. For networks, we'll think of it as a k-node subgraphs. So that's our mesoscale for the networks. And mesoscale analysis for networks has been very popular in network science community, starting from early 2000s. Network scientists try to look for basic small subgraph pattern that are kind of representing this common biological function of various complex networks you can find in the literature. Okay. So that's the network or mesoscale kind of introduction. And another concept that I wanted to tie together is this low rank concept. So basically, if you have a lot of data, in this case, each data is organized as a d-dimensional column vector, and then you have n of them. We say this data matrix is low rank if there are some latent basis vectors. There are of them in this case. So that you can represent each of these columns as a suitable linear combination of these columns of the dictionary matrix. Okay. In the network science case, there are a lot of different ways to formalize this low rankness of a network. But one classical way is using the community structure. So you have an n by n big adjacency matrix of a network, but we can say it's a low rank because when it has some community structure, size r by r or some 5 by 5 as we saw before, and this U is a matrix that assigns each node to each cluster, each community. So then you can you're really compressing this n by n network structure as this r by r community structure. Okay. So we've seen this example. So we were able to fit this stochastic block model to this big network. So we can say this network has like a rank 5, or at most 5. Right, but what if we try to do the same thing for this coronavirus network? So it's not really obvious. It was pure luck that my Python network drawing just gives me out this kind of already clustered picture. So usually your network picture is going to look random like this. So how do you fit these models into? Usually, it's a really hard problem. It's just not hard empirically, but theoretically, it's been shown recently it's impossible for a lot of real-world networks. So there was a recent PNAS paper that showed if you have some random network model that are based on this community structure, in more general, it's called a random dot product graph model, then it cannot model large number of triangles using small degree nodes. And that's some feature that you can observe in a lot of real world networks. So yeah, it's impossible to have this kind of global low rank structure or approximation of networks that exhibits this kind of feature. Okay, so that's one motivation to go to mesoscale. So we're not able to always do this global scale low rank approximation of the network. But what about at mesoscale? So if we go down to the subgraph level, can we still do that? So yeah, I want to make sense of this too. So we go down to the mesoscale, we're going to reconstruct our global network using this mesoscale structure. Okay, so we already seen this. So if you have an image, you can learn some this mesoscale shapes and then go back to the image and reconstruct the whole thing. And yeah, there's this is a classical literature in optimization and signal processing and so on. Okay, so we want to draw a parallel story for this one. So if you have a network, you can try to learn this basic subgraph patterns and then go back to the network and reconstruct it. Okay, and depending on the network, the type of this basic subgraph patterns, they differ, and they actually show this common network subgraph structure depending on different networks. For example, UCLA has a very sparse subgraph structure, and Caltech has a very kind of more dense subgraph structure. Okay, so there are three components. Okay, so I can slow down. There are three components that's needed to develop this network mesoscale reconstruction algorithm/theory. The first one is sampling. So for image case, the sampling was trivial because you can just sample a k by k window without any problem. But for networks, you need to sample a k-node subgraph. But in a lot of cases, the real-world networks are very, very sparse. So you cannot just sample k-nodes uniformly at random, and because that's not going to give you too many edges. So we need to develop some sufficient, a proper sampling algorithm. And this is the second one is if you reconstruct this, we already showed us some animation of how the reconstruction goes. And how can we measure? How can we bound the error of approximation, global reconstruction error, in terms of what you use at the mesoscale? So that's the second part. And the last part is how do we learn these basic subgraph patterns from a given network? So this is related to a lot of dictionary learning algorithms that I'm going to talk about. Okay, so for network sampling, I already mentioned the real-world networks are very, very sparse, so it's not very easy to sample k-node subgraphs. So we want k-node subgraph to be connected in some way. So what we propose to do is we want to sample a k path first, this red path, and then we're going to take the induced subgraph on it. Okay, so I want to sample a path of k nodes uniformly at random among all possible k paths, and then include all the edges in between the sampled nodes. Okay, so this red path is a path that I sampled, and these blue edges are additional detected edges on this path, and this is a k by k adjacency matrix of the subgraph. So these two diagonal lines, it corresponds to the edges along the path you sampled, and the additional pixels outside, it corresponds to the blue edges that you additionally detected. So in this case, you detected a big cluster, so this path is penetrating some small cluster around it. Okay, but this sampling of k path uniformly at random, that's also not a trivial problem. Okay, so a naive approach is okay, so this path becomes a Hamiltonian path of the subgraph you sampled. Right, so these are examples of the subgraphs you can sample in this way. So these are different, there's a social Facebook networks and the Erdős-Ürni, Barber-Shelbert, and Watts-Strogatz, and stochastic block model. At k equals 10, these are induced subgraphs at level 10. And you can go to the scale 20, then these are subgraphs induced on level 20. So depending on the scale, mesoscale parameter, you can see a lot of different kind of structures are detected. One thing to note is in the Erdős-Ürni case, you may think all the edges are random there, right? So they're completely independent, but you're actually conditioning on seeing a path. So that part is not random. So only the blue edges are completely random. Okay? Okay, so and if your distribution is very, very sparse, you're always going to see this path, and there are not very many extra blue edges. So that's why the subgraphs sampled in this way from UCLA and sparser distribution look quite the same. Yeah.
How do you ensure that you don't end up back at the same point?
Yeah, I'm gonna discuss that. Yeah, right. So the question is, how do we sample uniformly random this k-path? That's one problem. Okay, so let's start with the naive rejection sampling algorithm. So you can try to sample k nodes uniformly random, and then see if it forms a path. If it backtracks and then makes a cycle, just reject it. Okay, do it again, and yeah. So you do this until you succeed, and then you can return the whole thing. But this is going to be very, very expensive because if you have very sparse networks, the probability of a random k nodes forming a path is very, very low. Okay, so this is very expensive. So instead, we are going to use a Markov chain algorithm that samples a k-walk. This k-walk means it's a sequence of adjacent nodes, but they can backtrack, they can repeat, they can overlap, right? So it's very easy to sample this k-walks using Markov chain algorithm. I'll explain that in a minute. And you reject this k-walk, you accept this k-walk if it is a path, otherwise you reject it. But now the acceptance probability is much higher because you already have sampled the k-walk. Okay? All right, so this is how the Markov chain algorithm works. So you start with a k-walk, and then you can randomly evolve it to some nearby k-walk in some way. So then this random kind of path will walk around your network and then will return the subgraph detected. Okay, you can increase the scale parameter like this. And at 20, the type of subgraph you're getting is much more rich, and this k by k subgraph adjacency matrix is becoming also richer. Okay, so the algorithm we are using, there are two versions of it. So one version is inspired by Gibbs sampling in this classical MCMC literature. The other one is a modification of a random walk algorithm with Metropolis Hastings correction, and then we're thinking of this one red node or performing a random walk, and then every time it moves, we subsample the subsequent nodes. But there's a Metropolis Hastings correction so that the entire stationary measure is a uniform distribution that we wanted. Okay, so that's the algorithmic sampling part. And the next one is network reconstruction. Okay, I'm putting a lot of the technical details under the rug. All right, so it's very similar to network reconstruction. So if you sample a k-path uniformly random, you're going to get a subgraph like this, and you also get a k by k adjacency matrix for the subgraph, right? And then you need to have an oracle, low rank approximation oracle. So if you have an observed k by k matrix, binary matrix, there's some way that you approximate it by using some method, right? There's a linear combination of some other structures, like we saw before in the reference images. And you can do this for every single time of the Markov chain. So you can just keep doing it and average over everywhere. Okay, so that's how we do it. But this first sampling part is pretty expensive. So we can replace it by this MCMC sampling algorithm. So you can follow along this MCMC trajectory, and then you do this every time the Markov chain evolves. Okay, so this is how it works. So this is observed graph. And then you run your Markov chain inside the network. And every time a Markov chain steps forward, you're going to get a subgraph and an adjacency matrix. And if you have a way to approximate this adjacency matrix by some way, then you try to replace what you observe by your reconstruction at local level, and then try to patch them together. Okay? Yeah?
Is there an optimum choice for the length of Markov steps you take? Or is
Length of the path or
many
iterations?
nodes you include?
So, yeah, very good question. So I didn't mention, so how many times you need to run the Markov chain until you sample from uniform distributions? So it's closely related to the mixing time of the Markov chain. We weren't able to get exact mixing time, but if you fix the size of the graph, the Markov chain is irreducible aperiodic, so it mixes exponentially fast to the stationary distribution. And we showed the stationary distribution is uniform, but the exponent may depend on the size of the G. So we have an upper and lower bound, but it's nothing really sharp. Yeah. And for we show this Glover chain mix is very, very fast for dense networks, but for sparse networks, it's a big fat snake trying to move inside a very narrow channel, so it's going to be very, very slow. But this one is a kind of one single guy that are dragging all these subordinates, so it can make much faster. But every time you need to compute the rejection probability using metropolis hasting, so that each step is more expensive, even though you need fewer iterations for this pivot chain.
So you're making a continuous valued approximation to your binary?
Right. Yeah, that's right.
Are you doing some thresholding afterwards?
Yeah, later we will do some thresholding to compare binary to binary. But right now, your continuous valued weights, you can think of it as a kind of confidence of seeing an edge between the two nodes respect to the oracle you used. Right, so if you compare with the image reconstruction, so the sampling part was trivial. So you can just sample k by k window everywhere. But for the networks, we are kind of chasing along an MCMC trajectory. But other than that, it's very similar. Okay. Right, so the network reconstruction bound we have looks like this. If you have an original network with node set V and a weighted adjacency matrix A, we showed our network reconstruction algorithm is the iterative algorithm will converge to some limiting network on the same node set V and this limiting weighted adjacency matrix A hat. And we measure the distance between these two networks by using what's called Jacquard distance. So roughly speaking, it's measuring the number of edges that don't belong to outside of the intersection divided by the total number of edges. So that's the numerator here. That's measuring the edges that are not common to each other, and we divide by the total number of edges. Yeah. So we are showing that that's bounded above by product of two terms. This expectation is pretty reasonable because that's this bold X is the random K path you sampled. Okay. So if you sample a uniformly random K path, this A sub X is what you observe, the K by K matrix that you observe. And this AX hat is the approximation you used. So this is an average approximation error at mesoscale K. Okay? So if that's 0, then your global reconstruction is going to be perfect. Okay, but it's not going to be 0 usually. And also another factor is 1 over K basically. So K was the mesoscale parameter. So it says that even though you can if you have a slightly less accurate mesoscale approximation, if you can achieve a similar level of performance at a larger mesoscale, it's better for the global reconstruction. Okay, so that's what, yeah. Okay, and yeah, so this was in our joint work with this network version of the reconstruction algorithm. And it's relatively straightforward to generalize this proof method for the images. So it's about the same, but the prefactor, the scaling becomes 1 over K squared basically. So 1 over K appeared here because you're conditioning on seeing a path. So how many edges are you conditioning? So it's at most K edges, right? But for the images, you're conditioning to seeing in a window. And how many edges are there? That's K squared edges. So that's basically why the scaling like this. Okay, is there any question up to this? Yeah.
Why are these K walks good basis functions?
Basis function, okay, I didn't.
Because basically you're using them as basis functions for your expansion.
Right, yeah, that's a good point. So I didn't, it's actually a very good point. So why do we use K path? Like you can use K cycle or any trees or whatever template structure you can use. So there are some benefits of using this. So the first benefit is the sampled subgraph is always connected. But that doesn't have to be a path, right? If you use a tree, then you can always sample a connected subgraph. Another important advantage of this is, so your signals are graph valued, right? It's not a priori vector valued signal, and you want to apply some vector valued optimization algorithms. So you need to somehow vectorize this k-node subgraph so that you can apply this dictionary learning algorithm and so on. So that means you need to choose some ordering of the nodes. And once you do that, then you have a k by k adjacency matrix. But there are k factorial ways to order the nodes if you don't have any structure. But if you have a Hamiltonian path, that already gives you a priori path node ordering. So this is a canonical, I mean, of course you can still shuffle the order of the nodes, but then the adjacency matrix will look very random. But if you use this path ordering, that's why we see this nice structure. There's a common spine, and these clusters will mostly look like this already well-clustered like squares in this picture. Yeah. Yeah.
I also have a question. I'm curious, like, how important is this uniform sampling of the k-paths? Like, if you just, did something very naive, randomly pick a node, then randomly pick from the neighbor set, like without any adjusting to make sure you're converging to the uniform distribution, how bad is that for the reconstruction?
I mean, that's also a very good question. So the reason we chose the uniform sampling was, I mean, if you don't know anything, it's a uniform is like unbiased as possible. And our goal was to get the best global reconstruction. So for that, you cannot really treat some region preferably to the other region. So you need to sample like almost every region of the network so that you reconstruct everywhere. But if your interest is more in the particular region of the graph, then you can just keep sampling subgraphs a lot in that area. And if that's what you wanted. For example, so you can just do like just random walk. Start a random walk at any point. Do a k-step random walk. And if that's a path, then maybe that's your sample. So this path is not going to be uniformly distributed, but it's very easy to compute. So if you don't have any strong reason to use uniform sampling, then you can just use any other distribution too. Yeah, but where you sample is going to affect the type of dictionary or basic shapes you learn. So for example, in the images, if you keep sample this like kind of umbrella, then your basic shapes, the basis you learned from these samples will be perfectly explaining this umbrella shape, but it will be very much struggling to represent any other area. So that also depends on what part of the object you want to learn from. Okay, so now with that we have this upper bound. And we mentioned we're going to use a very simple linear model of this low rank approximation oracle. So if you have an observed k by k matrix, we approximate it by some linear combination of some even more basic subgraph patterns, L1 through LR. So the question is, how do we learn this? How do we learn this from the given network? And this upper bound suggests a way to do that. So we want to learn this L1 through LR so that this expected reconstruction error at mesoscale is minimized. So it suggests us an optimization problem. Okay. So this is a network dictionary learning problem. So you're trying to optimize L1 through LR. It's a weighted k by k matrices. So that if you sample a k path uniformly random, you try to minimize this expected L1 reconstruction error of the sampled k by k matrix by the best linear combination of them. Okay, so that's a very traditional dictionary learning algorithm. The only main difference is the sampling part is using some graph-informed sampling. So it's not the uniform sampling is not very straightforward. We also want to use non-negative constraints, non-negative coefficients, so that, okay, so I mean, you can use PCA or any kind of dictionary learning algorithm, but if you restrict everything to be non-negative, then you can still interpret this L1 through LR as a sub-network or subgraph. So if they have like negative entries, then it's kind of hard to interpret that as a subgraph. But so that's beneficial to have non-negativity constraints. So it becomes a classical online dictionary learning problem or online non-negative matrix factorization problem. But the samples, the signals you're getting is not necessarily IID. So I mean, you can have it IID, but it's very hard to or expensive to get IID. But it's much easier to get correlated samples from the Markov chain. So yeah.
Why does it need to be online? I mean, you could sample these things beforehand. No?
Right. Yeah. So I didn't really motivate that too much. So yeah. So even easier way to do this problem is you sample a lot of patches, a lot of samples, a lot of subgraphs, and then just form a big gigantic matrix to be factorized. You can do that, but you need to store all of them in a big memory. But in an online way means you sample 1 or maybe 10 subgraphs and process that, and then just throw it away. and then sample another 10, so that you can learn from almost infinitely many samples with very limited memory. So that's an advantage of doing it online. And also, empirically, the convergence speed is much faster if you do it this way. Yeah. Okay. So these are some examples. So if you have an image, you can learn this basic shapes like this. That's how it look like. As someone in the audience pointed out, the basic shapes have this shapes, right? So like a straight lines, and it's a fundamental structure of this network image at that scale. And that's what we do for the Caltech and UCLA networks. And each graph has a non-negative weights, so that we can still interpret that as a kind of or latent subgraph. So we call that latent motifs. It's not an actual subgraph, but it can non-negatively combine together to approximate any given subgraph. Okay. There are some examples, other networks, and depending on the different scale, you can see how these latent motifs change their structure. I'm only showing the first two most dominant latent motifs. So they're kind of telling us the most fundamental subgraph structure in the network. Okay, so I still have some good time. Okay, yeah. Right. So I want to talk about what is the algorithm to learn we use to learn these subgraphs or dictionaries. Okay. Oh, okay. Before we go there, let me talk about applications. Okay. So what is all about this good for? So as a starting point, we have an original image A, and you can reconstruct this image using any kind of given dictionary. So first, we can use this completely randomized dictionary D to approximate this image A at local level and an average to get a global reconstruction. And it's very blurry, and the colors are lost because the original dictionary didn't have any information. But the reason you still get some basic shape is because you are operating at a local scale. So when you're sampling, you're trying to approximate the same pixel multiple times at different locations, different angles. So that's why you can still get some basic shapes like this. But if you use this dictionary, the sharper dictionary learns from some other image that has this diagonal or straight lines like that, you lost the color information, but you still got very nice, sharper looking images than before. And yeah, I had enough time to run my algorithm so that there's no like black area here. Okay. Right. So I'm gonna do the same thing for networks. Okay. So the analogy is there. So we have a network Y. I want to reconstruct this network Y by using this dictionary of latent motifs we learned from completely different network X. Okay. If the reconstruction is good, that means the subgraph structure is rich enough so that it can explain the network Y. Otherwise, it's not a good fit. Otherwise, they have very different structure. So let's look at the Caltech. So we are reconstructing Caltech from a dictionary learned from different networks. There are 8 networks, 4 Facebook and 4 synthetic. So the best approximation is, of course, when you learn the dictionary from Caltech itself, right? So obvious. But what's surprising here is, so this vertical axis is a Jacquard reconstruction accuracy. And you get above 80% accuracy by only using 9 patterns, 9 basic patterns. Okay, so, and this is using 20 node subgraphs. So the mathematical dimension of the subgraph space of sampled in this way is 190. So it's just count number of independent pixels, except the pixels that are conditioned by the path. But we don't need 190 to approximate this Caltech. We don't actually, like 9 is good enough. So that kind of tells us, even though it might be hard to approximate your network at a low rank, at global level, if you go down to the mesoscale level, there's not so much variation in the subgraph patterns you see. So that's why you don't need that many different patterns to approximate everywhere in the network. Okay. Now, of course, if you increase the rank of the dictionary, the accuracy will increase also. And another interesting point is what network does the worst for reconstruction. For example, this guy is Erdős-Ürni random graph. So if you learn these basic shapes, basic subgraphs from Erdős-Ürni and try to reconstruct Caltech, it performs the worst in this case. So that means the subgraphs you learn from Erdős-Ürni is not really a good fit for Caltech. So it's a way to test your random network model at the subgraph level. Does it fit well or not? Okay. In other words, on the other hand, this stochastic block model, this blue one, it does very well for this context. And it depends on all the other networks. Okay. Any question? Right, 10 minutes. Okay. So let's try to get some insight of what this low-rank mesoscale approximation really does for the networks. So I plotted this degree distribution for the reconstructed network. So the shaded histogram is a degree distribution of the original contact network. And these lines are degree distribution of the reconstructed network. They are thresholded to make it binary using different number of leitmotifs. So we saw at rank 9, we already got 80% accuracy. But if you look at the degree distribution, it's actually cutting off the large degree nodes, or maybe keeping the nodes, but cutting off the edges so that it doesn't really allow to have a very large degree nodes. And if you increase the rank, it seems like it's getting or recovering like a more and more large degree node, like a more edges for the same nodes. So in some sense, this low rank mesoscale approximation is kind of giving you a degree truncated version of the original network. Okay. Well, that was the case for Caltech, but it's not so clear for coronavirus or Facebook. So it's articles 25, it does pretty good job in approximating this degree distribution. Maybe because these two networks are even more low rank than Caltech. Yeah. So yeah, there are 100 networks in this data set, and Caltech is known to be most eccentric, not eccentric, but more a kind of outlier. It has a richest scale structure in comparison to the other networks. Okay, and this is another main application of our method. So if you have a network, let's choose, can I write somewhere? If you have a network, let's choose some small region, and let's add some edges according to some rule, and these are all false edges. And you throw in some algorithm to figure out what are the false edges. Okay, you're given the same node set, but now edges could be the original edges, and also the false edges. Okay, you never know what region you added. Okay, so that's the network denoising problem. If you corrupt your network like this, can you denoise or detect the false edges you added later on? We tested a lot of different methods. So these 4 are very classical node embedding algorithms. And these 2 are more modern. It's coming from this node2vec or deep walk network embedding literature in the recent machine learning community. And the last one is our method. So it looks like our method performs pretty well in this particular test. I need to admit, there are instances that our method doesn't work very well. So this is a kind of best case. But the reason that our method works well in this case is because, so this corrupted network is an input for your algorithm. And you can try to extract this L1 through LR from this corrupted network. But because your corruption is localized, these L1 through LR are not very much affected by this corruption. So they are meant to be representing subgraphs everywhere in the network. And there are still some clean regions in the network. So maybe that's a reason that our method performs particularly well for this type of task. Okay, so I have like 4 minutes, 5 minutes. Okay, so all right, so in the remaining time, I'll just briefly talk about the algorithms and theoretical guarantees for the dictionary learning part. So we encountered this expected loss minimization problem along the way. So we want to minimize this expected loss function with respect to some parameter, and the usual way to do this is to approximate this expected loss by some empirical loss, because in our case it was very hard to sample exactly according to the distribution we want. So if you have a lot of samples, then the empirical distribution function approximates the expected loss function. Okay, so let's start with the image case. So this is a version that does not use any stochastic algorithm. So if you have an image, you sample this k by k window, vectorize as a k-squared dimensional column vector, and then just collect everything and do a non-negative matrix factorization. Right? Then the first dictionary matrix consists of k-square dimensional column vectors. So you can reshape this k-square dimensional basis vector back to k by k. So these are the basic shapes you learn this way. But you can also do this in a much more memory and computationally efficient way. So you sample a lot of them, and you don't wait, you form this gigantic matrix to be factorized. Just stop at some early point, and then pre-factorize that. And then you're going to get a second round of this samples. And there's a way to update the previous round dictionary according to the new input. So that's an online matrix factorization algorithm. So sampling and learning are happening back and forth. So your memory should be large enough to fit only this size, not the previous, this big size. Okay. Right, so for the network case, it's the same. We run this Markov chain sampling algorithm in the network. That will give us this k by k adjacency matrix. You can vectorize it to form this similar matrix of signals. And you can try to learn this dictionary matrix online like this. But the main theoretical difference is these mini-batch matrices are now correlated. They are driven by this underlying Markov chain. So we need to be able to learn from this correlated stream of data. So that's the main theoretical motivation. Okay. Okay, I'll skip the algorithmic details. So this class of algorithms we use is called stochastic majorization minimization. It's a general version of EM algorithm used in statistics. So they are first developed for IID data. What we showed first was we can still use the same algorithm for correlated data samples. Okay. So this is a non-convex constrained optimization problem, so it's hard to guarantee global convergence to the global minimizer, but you can still show convergence to, almost sure convergence to stationary points. That usually is good enough. It was shown previously for IID data, but we extended it to data that are given by functions of some underlying Markov chain. And later, or more recently, I updated this work so that for a more general class of algorithms, now we have some rate of convergence results. So you know how many iterations are required to achieve epsilon accurate station point for these algorithms. Okay, there are some tensor extensions. Yeah, so I'll maybe talk about this for the last minute. So in all our instances, our data, we had to vectorize our data. Whether it was k by k or k by 3, we always vectorize it and apply some dictionary learning algorithm. But can you kind of keep the original tensor shape and just work with it? For example, if your data in stream has 2 modes, can we try to learn some basic rank 1 tensors so that some combination of them can express each of the slices? Okay. So the basic method of tensor algorithm. Yeah. So your data is in stream coming in, and you try to learn this basic shapes, basic building blocks, but we further assume they are rank 1 tensors. And it's equivalent to learn this R factor matrices. And it's called the CP decomposition of tensors. So we have a tensor version of this dictionary learning algorithm that we recently showed. This algorithm is also convergent for IID and also for function of Markov chain. And the same rate of convergence result applies for this. Okay, and this is a plot that shows it's a comparison of this offline version of tensor decomposition algorithm and our online version of tensor decomposition algorithm. The lower ones, the faster ones, are all different instances of the online algorithms. Okay, so there are some tensor extensions of this dictionary learning. So if you have temporal networks, you can think of it as now your subsample is not a k by k adjacency matrix, it's k by t. There's a time axis together. So you can try to learn this basic subgraph shapes and how they change in time. So that's an application for tensors. Okay, I guess that's it for my talk.